Before we have provided motivation for studying the indexing in this section, as well as provide some examples for index tables we have in the real world, right? And here we will provide a theoretical definition for an index. What is an index? So an index on a file speeds up the selection on the search key attributes. In other words, this index can help us speed up the selection, the search of some desired attributes, right, in database systems. Here, the search key equals to any subset of the attributes of a relation. Because if you still remember, right, we do a selection with some conditions, right? This condition describes the matching desired properties of the attributes. So the search key is not the same as the keys. Before we mentioned the key is an important concept for tables. However, search key is different from keys. The search key is some desired search properties or attributes. It can be any subset of attributes we have in a relation. Like here, we want to search for some like customs whose gender is male. This male is not a key for a person, right? However, it can be a search key for the search process. It can be any subset of the attributes of a relation. So from the given a search key, we can return a bunch of records matching the keys, right? Matching the search keys. So therefore, the entries in an index table can be represented as a tuple with both search key as well as records matching the search keys. The header key denotes the search key. It is any subset of attributes of a relation. This R denotes the record or the record ID or IDs matching the search keys. In other words, given a search key, we can know which record matching the search key, and we can also access to the full record via this R, this record IDs or the records. This is the data structure we can have for the index or index tables. We have entries to be this tuple, key, and R, the search key and records. And in the database systems, we have different kinds of indexes, and we'll provide the categorization of these indexes we can have for database systems. The index can be either clustered or unclustered. Cluster means the records are sorted in search keys, search key orders. Or the index can be unclustered. In other words, they are not sorted. You can follow me, right? Before we show you with the example, right? If you still remember, we will search for some desired numbers. If this list is sorted, then it will be clustered. If it's unsorted, it will be unclustered, right? And another type of this categorization of the index will be depending on the density of the index. It can be either dense or sparse index. Dense means each record has an entry in the index table. Sparse means only some records will have this entry in the index table. We'll provide you with some examples later. So this is a different dense tables versus sparse index tables. And we can also have a primary and secondary index. Primary is for the primary search key. Secondary is on the secondary search keys. And some textbooks also interpret them differently. Besides these types, we can also have the B+ tree hash tables, which are also different types of indexes we can use in database systems. So this is about the categorization of these indexes. We'll provide you with some concrete examples, the clustered and dense index tables. So here, on the left-hand side, it denotes the index table. So inside this index table, we have a bunch of entries. Each entry is represented as a tuple, right? It's a tuple with both the search key as well as the record or the record IDs. So it's similar here. Here in the index table, we have both the search key as well as the index ID. We represent this index ID as a pointer. It points to a specific tuple in our tables in the database systems. So the left-hand side is the index table, the index. The right-hand side is the concrete data we store in our database systems. So given a search key, we can find a pointer pointing to a concrete data tuple storing the data matching the search keys, right? Now given 10 via this pointer, right, we can access the data tuple with that 10 as the desired attributes matching the search key, Similar for 20, for 40, for 80, right? So by checking this index table, we find this table is sorted according to the search key. We have 10, 20 to 80, right? It's sorted. Therefore, we can say this index table is clustered. Also, we find this index table is dense because each record in our database system will have an entry in the index table, right? It's dense according to the previous definition. So you see, if we have so many different data tuples in a table, then the index table we have to create will be huge, right? It will affect the efficiency for us to do the search actually. It's the same if we have 1 billion records in a table, then the number of rows in the index table will also be 1 billion, right? If we build a dense index table, it will be so huge, and the search process will also be very slow. So another category of the index table we can create is called a sparse index. So given the data tuples, we have 10, 20, 30 to 80. However, we have an index entry for 10, for 30, 50, 70. We don't have the index entries for 20, 40, 60, 80. Right? However, these records as well index table are still sorted. In other words, it is a clustered and sparse index. So for the data records with entries in the index table, we can search them very fast, right? So given the 10 desired attributes, by checking this index table, we can know where to find the data tuple matching the search key. Now from 10, via the pointer, we can go into this tuple, right? It matches the search key. However, later if we plan to search for 20, how can we do this? We search in the index table, we find we cannot identify any numbers matching the 20 as the search key, right? However, for these kinds of index tables, it has to be clustered. In other words, it has to be sorted. Therefore, instead of searching 20 directly, we can search for 10 first, right? 10 is smaller than 20. So from 10, we know this one is sorted. We're going to, from 10, this record we can go downward because we know it's sorted, right? Going down, it will increase the search keys. From 10, we can going down, then we can find 20, right? Because this one is sorted, therefore we can do the search in this way. We can search a number which is smaller than the desired attributes if it is not in the index table. It will be similar for 40, right? If we plan to search for the 40, we can find a number which is smaller than 40, we can go to 30. 30 is smaller than 40, we can go to 30 first and going down to find 40, right? It will be similar for others. This is another kind of index table we can create. It's clustered and sparse. And for index tables, actually we can have some records with the same search attributes, search key attributes. Because we mentioned that the search key is another keys. There can be any attributes in a relation, right? In other words, for tuples in our table, they may have the same value for search keys. In this case, how can we build an index table to help us? We'll still build a dense index table, right? In other words, for all the numbers in the data tuples, we will have one entry for them. However, here we allow different tuples have the same value for the desired search key, right? Now 10, we have 3 records with 10 number, right? We have 3 records with 20 as well. Then in the index table, we can assign this pointer pointing to the first record matching the search key, right? If we plan to search for 10, then we have 10 here. Its corresponding pointer will point to the first record in the data tuples in our database system with 10 as a value, right? Similar for 20, it also points to the first 20 here. Therefore, later on, if we plan to find the data tuples with 10, we can go to the first record with 10, and also going down, we find they are all the 10s. And until we're reaching a number which is larger than 10, right, we will stop. In this way, we build a cluster. It is sorted, right? All the dense index table with duplicate keys. You may wonder if this cluster is important or not. So the cluster index can be very helpful. However, in the real world, it's very hard to maintain a cluster index. The main reason is because data tables we have in the tables can be unsorted, can be mixed together. So normally when we do the search in our database systems, we want to search for some desired attributes, and these attributes can be different from the primary key, right? It can be any attributes in the relation. And now, for these kind of cases, we have to build a very dense index tables. The main reason is because for these searching keys, for the tables we have in the database systems, they have different values, right, for the desired search keys, and they are also unsorted. Because we don't have any orders, right, for these numbers or for the records on these desired search keys, therefore we have always to build a very dense index table to help us, because we don't have any orders for these desired search keys, right? Because of this reason, the values, the orders have been broken for the real world database systems, and we have to build very dense index tables. Okay, so these are the different examples of these index tables we can create in database systems.